Thank you very much. So happy to be here in Chapman in California and to speak to you about these issues. So we are asked about whether philosophy may be useful to science and vice versa. So from what I understand, the answer depends on how we understand usefulness, and also how we understand science, philosophy, and their conjugation and their difference. So I will first interrogate the notion of usefulness. So I begin with a personal memory. Very long ago, in a kind of former life, I was teaching mathematics in high school. And I was supposed to teach the chapter called Continuity and Limits. So I was supposed to teach that to a bunch of teenagers from eastern outskirts of Paris. And I was under the influence of a former professor of mathematics of mine, who used to say us, I challenge you to teach continuity and limits without introducing the notion of filter basis. So it was very difficult for me to go beyond the authority of this professor. So I was indeed trying to inflict my 16, 17 years students the definitions of filter and filter basis. And I remember very well that at some point, one of them, and it was not the most rebel one, he was trying to be friends with me even. And he asked, what's the use of these notions? So the question of usefulness came in my classroom. Scandalous. Such question had never arisen before. So could I really think that my pupils had thought that everything I had told them was useful? I don't seriously believe that. Because useful can be understood as useful for spontaneous life of an adult not engaged in a mathematical profession. If you understand useful in that way, so everything I was teaching was not useful, most likely. And my pupils knew that very well. And so they were used to being taught not useful things. Still, my student, the one who asked the question, felt something, and I think he felt rightly so. He sensed probably that I had exaggerated, and maybe he heard something insecure in my voice, or maybe simply he had identified the content, filter basis, as something different, something not easy to include into the box of usual boring mathematical contents. So if my interpretation is correct, he was understanding useful as meaning well integrated in some whole. So far, we are discussing the usefulness of mathematics themselves, or mathematics itself. But I think more deeply, we have to recognize that we don't know exactly what's useful and what is not. And I will make a comparison with what Wittgenstein says in his lecture about ethics about good. Wittgenstein, in this lecture, in this famous text, observes that most often we qualify something as good because it stands in conformity with some model. A good aviator is someone close to the aviator model. And then Wittgenstein goes one step farther, and he says that something ethically good should be something absolutely good, so without reference to any particular model. So I think when we use the adjective useful, most often we think something as useful because we see that as helping to reach some unquestioned goal. For example, working out is useful for avoiding cardiac conditions. I've heard that. So I don't know if you are convinced, but it's often said. But so here you could try to introduce, like Wittgenstein, an absolute notion of usefulness. So absolutely useful would mean useful with respect to absolute ends. And the distinction between relative and absolute ends also already appears in Aristotle, in Nicomachean Ethics. And I've heard that some Christians, completely convinced Christians, consider as really awful only what helps salvation. So you need this absolute end in order to truly speak of usefulness. That's I wanted to underline that useful is not an easy notion. That was my first consideration. Then I come back to another way of thinking of philosophy showing useful for science. Maybe some people have in mind an actual scientific development incorporating a philosophical segment at the technical level, or vice versa in the symmetric case. So when we imagine that maybe philosophy is useful for science or science useful for philosophy, we are thinking of a technical inclusion. So it's a very high demand, but I think at the beginning, when you hear the question, that's how you understand. But then there is also a difficulty with technical. Do we really understand what technical means? It derives, technical as an adjective derives from the substantive technique. So in many contexts, a technique seems to be a name for any kind of black box providing some outcome on the basis of some kind of prescribed input. So we have a technique each time we have that kind of black box, which is going to produce the expected outcome if nourished with the correct input. But there are other uses of the word technique or the adjective technical. Here comes another example, which is not personal, but which is that kind of example I love, which is an example taken from a TV show. It's an American TV show called Without a Trace. I don't know if one of you saw it. And it had 7 seasons. And I'm speaking about the last episode of season 7. And so in this episode, you have a dialogue between the 2 main characters, Jack and Sam. And during the 7 seasons, there was always a big issue. Are they going to end up together? You know, you have to understand that there is something sentimentally important here. And so Sam, first Jack speaks to Sam, and then Sam speaks to Jack. And Jack says a lot of things. He explains where he is at the moment. And Sam asks, "Are you breaking up with me?" And he answers, "Technically, yes." And then she explains how she is in her life at the moment. And he asks again, "Are you breaking up with me?" And she answers, "Technically, yes." So you have another use of technically here. So we understand that technically means here that if you stick to the objective level of verification, the relationship comes to its end. Still, both Jack and Samantha, maintain that this facet of meaning is not enough, or maybe even it betrays the true meaning. So technically, here means if we stick to the verification level or to the operational level. But maybe one could reply here that it's a classical analytic claim that there is no semantic content beyond such level of verification or making operational. It's called semantic behaviorism, I've heard. So that was a kind of TV show sentimental example. Then I have another example, which is that we use sometimes the adjective technical in order to describe some parts of mathematical discourse. We describe some part of mathematical discourse as technical when we feel we attend a complexity which is purely combinatorial, purely mechanistic, instead of being conceptual. So we may remember here that to replace computations by concepts was a Bourbakist slogan, a promise of new mathematics. Anyway, objection to this consideration, we know that even within alleged conceptual parts, you can have a lot of complexity, a lot of complex articulation. I take the example of the introduction by Grothendieck of the notion of scheme. It takes a lot of pages and it's highly technical. So, you know, my first lesson is that we don't exactly know what useful means, and we don't exactly know what technical means. And then I come to the other part of the presupposition to interrogate, which is science and philosophy. So I think there is a possible disagreement about science, about philosophy, and about their relations. To begin with, there is no universal agreement about what philosophy is. I think there was never any, but nowadays, it's completely blatant that there is no agreement because of the international divide between analytic and non-analytic philosophy. So I would like to lead you through two observations about mathematics and philosophy by two French philosophers of mathematics, Albert Lautmann and Jean-Toussaint de Sainty, because they said something which I'm going to use later. So first, I begin with de Sainty. In his essay, Qu'est-ce qu'un problème? What is an epistemological problem? De Sainty distinguishes between three kinds of problems. Problems of the first kind, and he takes the example of, are we able to prove that any set supports a well-ordering? Problems of the second kind, and he takes the example, how could we overcome the paradoxes having emerged in set theory with Russell and Cantor? And then comes problems of the third kind, and the example for him is, which status should we give to the choice axiom? So problems of the first kind for de Sainty are strictly internal to some proof system. It's a technical issue, mathematical issue, an ordinary mathematical issue to know if we can prove within set theory that any set supports a well order. Problems of the second type are different because it's about overcoming the paradoxes, and these paradoxes, we have them in our current system. So it's about defining a new system. So it's about a theoretical gesture introducing a new language, a new logical system. But what de Santi wants to call an epistemological problem, properly speaking, is a problem of the third kind. So his example was, which status are we going to give to the choice axiom? And he sees that in the choice, endorsing the choice axiom, we have two levels of difficulties. One level is the logical one, and we are wondering whether adding the choice axiom is going to change something in the logical situation. And de Santi concludes that proofs from Gödel and Cohen, as it is well known, have answered such question. They have shown that adding AC or its negation does not change the consistency issue. And so that's the first part of the issue. But then you have the other side of the issue, which is what introducing the choice axiom makes possible. And de Santi privileges the formulation of the choice axiom, saying that the product of non-empty sets is not non-empty. And he observes that this asserts the existence of an element, on an element of a product of non-empty sets. And someone could say here that it's not enough to assert this existence. We need we need to know how to construct it. And that's why he concludes that the issue is not technical. Otherwise said, following problem: is non-contradiction a sufficient criterion for mathematical existence? Does not seem to allow its coding inside some language homogeneous with formal mathematical language, within which we could posit it and solve it like a first-kind problem. So de Santi seems to understand problems of the third type or of the third kind as problems unlikely to be brought back to the technical level or to the proof theoretical level. And in his analysis of the choice axiom problem, he comes back to the Brouwerian question. So is non-contradiction a sufficient condition for existence? Is exactly what Brouwer says in one of his famous Vier Sätze. So what de Santi calls an epistemological problem is a problem standing in principle beyond any technique. And we have no doubt that what he calls here epistemological also means philosophical for him. So it's a very traditional way of defining philosophy, that to define it as non-technical. And it's completely debatable for quite clearly. But if you accept this definition, and if, like de Santi does, you also accept that, surmise that mathematical developments are deductive developments inside some proof system, so that they are technical. So it seems to mean that there is no possible usefulness of philosophy for mathematics because of this technical difficulty. Something non-technical cannot be inserted in a technical context and still being helpful to this technical context. Another thing which shows in this discussion from de Santi is that what interests de Santi naturally, what he's naturally interested of, is the foundational entanglement between philosophy and mathematics. he already sees it, and that's what interests him. I come to Lotman. So a great part of Lotman's contribution is about how mathematical change happens. It is well known that French school has considered this issue of mathematical change as more important than the issue of securing mathematical truth. So according to Lotman, mathematical advance is governed by what he calls ideas. And in his philosophy, these ideas are officially connected with Platonician ideas. Each one of these ideas may be labeled by a couple of terms determining a semantic axis. He gives the examples of essence, existence, continuous, discontinuous, local, global. And in Lotman's vision, actual mathematical theories give precise content to the poles of an idea. There are each time two poles, and they express a conception of how the two poles relate. So there are theoretical incarnations, embodiments of the semantic axis named by the idea. So new mathematics happens when a mathematician lays down a new framework for writing down the content of an ideal tension. So there is a tension between local and global. There is a tension between continuous and discontinuous. There is a tension between essence and existence. And each time new mathematics happen, each time someone is writing down a theoretical context within which this ideal tension takes some explicit sense. So Lotman says two things which may be felt as contradictory. First, ideal contents dominate actual mathematical theories because history of mathematics sometimes show successive ways of theoretically covering the same ideal tension. So, for example, a topological approach may have changed the way of framing the continuous, discontinuous tension as Lotman understood it. But he's not, what he calls the continuous, discontinuous tension is not exactly that, but could have been. So I'm not true to Lotman in my example. At the same time, Lotman says that the ideas are not transcendent with respect to actual mathematical theoretical development, because ideal tension has no other explicit expression than in actual mathematical developments. So, you know, ideal tension depends on actual mathematics, because it's only in actual mathematics that you can grasp something. But also, these ideal contents dominate actual mathematical theories, because one and only ideal tension may be assumed in successive mathematical developments. So for Lotman, philosophy of mathematics, so I introduced something which was absent of, which is implicitly rejected in many interventions I heard here from this morning on, which is not only philosophy and science, but philosophy of. So Lotman, he sees philosophy of mathematics as having to comment on given theories, and he's trying to do that with theories which happened, which emerged exactly at the moment where he was writing and living. And so the task of philosophy of mathematics would be to comment on these theories, on mathematical theories, by showing how they deal with ideal tension, how they express it. So it seems to be a hermeneutical task. It seems to be that philosophy's contribution here is interpretative. But no, Lothman, I told you that it's the task of philosophy of mathematics, but Lothman doesn't say exactly so. He rather repeats mathematical philosophy. So for him, this is not philosophy of mathematics, but rather mathematical philosophy. And he says that the work of mathematical philosophy is not to exhibit a logical metaphysical content behind mathematical formulation. It is rather the work of understanding the structures shown in mathematics as a way to elaborate some dominating ideal tension. So such work, the work of mathematical philosophy, adds to mathematics a new layer of intelligibility. Lothman says that it is a different spiritual experience. So it's an activity of deciphering within mathematical activity something that animates it and gives motivation to it. As I said, it looks like a hermeneutics. It celebrates mathematical achievement as at an ideal and philosophical level, such reading being clearly mathematically unnecessary. We don't need that explication. So with this performance of what Lothman calls mathematical philosophy, we don't get exactly philosophy showing useful to mathematics, at least technically. But isn't it in some other sense useful to celebrate the mathematical achievement of elaborating some ideal tension? I think it could be said it is. At least if we think we should endorse and enjoy our cultural sedimentation. And this means entering the point of view of what I call philosophy of culture. We don't only live within such and such culture, we have to be able to enjoy and endorse every part of this culture, which sometimes means to be able to celebrate what happens in such and such region of our culture. So here I would like to add two ways of defining philosophy which have been mine. One which appears in a book published in 2008 is that I define philosophy as the extension of the mathematical project. And the mathematical project, I characterize it as the project of universal classification. Only mathematics does that with what I call objects, which are detachable objects able to be treated logically. And the extension which philosophy is meant to accomplish is the extension of this project of universal classification from the area of objects to the area of things. And things, what I call things, it's taken from the famous quote of Shakespeare, you know, Hamlet speaking to Horatio and telling him there are more things under heaven and on earth, Horatio, than are dreamt in your philosophy. So things here means any kind of conceivable entity, even if it's not detachable, even if it's not submittable to logical treatment. So that's a first way of defining philosophy in connection with mathematics, but as an extension of it, which I have offered. And another one is to define philosophy as what I call an ethos. So an ethos, roughly speaking, I'm not going to explain deeply all this, but an ethos is what I call a region of a sense region. It's a region inside of which some meaning is shared. And so each time there is an ethos in this approach, there is a table of the law of the ethos, which had to be written, and had to be written down. And I have tried that. I have tried to define all the injunctions that you have to observe, to obey, if you want to show as a philosopher. And I cannot avoid here the difficulty of the distinction between analytic and non-analytic philosophy. So I have two propositions. I have first 8 injunctions which characterize philosophy in general, which means also seen from the non-analytic point of view, and 6 injunctions which characterize philosophy seen from the analytic point of view. Now I come to philosophy of science. So there is a difficulty connected with the relation between philosophy and science. And another part of this difficulty is the notion of philosophy of science. Is philosophy of science a subspecies of philosophy? I think that for many people, after the Vienna Circle, philosophy of science is rather a subspecies of science. So if philosophy of science is a subspecies of science, then philosophy of science can be useful to science only as a knowledge tool. But reading the text of the Vienna Circle philosophers, one gets the impression that the questions they address are completely different from the ones worked at by science. So it looks like unlikely that one would be a tool for another. Another difficulty, which was already mentioned, is that this issue of the relation between philosophy and science, is philosophy able to be useful for science or science for philosophy? It cannot but vary with concerned science. For example, is this relation going to be the same if our science is logic or computer science, or when it is mathematics? I've taken here logic and computer science and mathematics are things, disciplines quite close one from the other, but still the relation with philosophy is not clearly the same. And even more when it is physics or biology, or if we have in mind human science. And inside human science, there is a special case of linguistics and economics. Economics was already arising in some of our discussions because both claim to have a more obvious connection with mathematics. So in what follows, I shall focus only on the case of mathematics, which is more familiar to me. So I am beginning to say one or two things about the case of mathematics. So now my question is philosophy able to be useful to mathematics and vice versa? So I want to start from what we may observe as a kind of mixing between mathematics and philosophy. And I would say that we have two kinds of mixing. We had what I already described as foundational entanglement, because the discussion about foundations has become, as we know, since 20th century, largely technical. It now involves at least logic, set theory, arithmetic, computer science, and category theory. Each of them is a candidate to be a branch of mathematics. So there is an intent, there are a lot of things here which may be named by some people as philosophical, and some other people could name them as mathematical. And one of Karin's questions was centered on that issue in the case of logic. This entanglement, the foundational entanglement, was clearly what de Santi was dealing with when defining problems of the third type. And then we have this, what I call the strategic entanglement, because some mathematical contributions are seen willingly as philosophical by themselves. Sometimes it is because they amount to a self-reflection of mathematics. Sometimes it is because they universalize something, or sometimes it is because they bring some guidance. So I think Lotman's conception of dominating ideas is related to strategy, because in his conception, improving our understanding of ideal tension is a motivation for new mathematics. So do these entanglements promise any usefulness in either direction? So I will try to deal with this question by looking at two examples. The case of what I could call non-standard non-standard. So I'm referring here to a specific school of non-standard mathematics, which was French-American, mostly. Other nations were involved. But speaking here, French-American is the most important for me. So there was Edward Nelson, who was directing the Princeton Department of Mathematics at some point, and Georges Reb, who was a mathematician in Strasbourg, having been very important in what is called the trajectorial school on differential equations. That's my first example. And the second example is category theory and Grothendieck's contributions. So I start with non-standard, non-standard. So this special school of non-standard mathematics investigated the possibility of getting the non-standard effect, which is having infinitesimals or having infinitely large numbers, in a quicker and simpler way than Robinson with his enlargements. So it was to make the non-standard more comfy for mathematicians. Ultimately, Reb connected that effect with Brouwer's conception of a constructive level of mathematical objectivity. So the story I'm telling you has some important steps, and a very important one is Nelson's paper in 1977. Internal set theory was the title. And then we have a paper from Reb in 1979, non-standard mathematics, 60 years old. And then we have two books published by Nelson in 1986 and 1987, which were called Predicative Arithmetic and Radically Elementary Probability Theory. So the issue of finding new ways of getting the non-standard effect was at first sight mostly a foundational one. The question asked was, which foundational resources do we mobilize for having infinitesimals? And how can we be confident that introduced discourse is consistent? So Robinson's enlargements, as it is well known, happen in ZFC, and they produce elementary equivalent models of concerned theories. So you are applying the enlargement technique to a specific part of mathematics, and you are producing an elementary equivalent model, which justifies, for example, the principle of transfer, the transfer principle. In Nelson, we came to something which happens at the level of sets theory in general, at the global level of ZFC. You don't have to produce an enlargement for each particular region of mathematics. You define, so to say, an enlargement of ZFC. But this enlargement is not exactly an enlargement. It's called IST. It's a new set theory, which is new in the sense that it has a one-place predicate, which is added to the language, which is ST. And the meaning of ST is implicitly given by three new axiom schemes, I, S, and T. So you know, IST, the title of, the internal set theory is the title of the paper, but IST has many values here. So in Nelson's approach, we have already infinitesimals in R, in our classical R. We don't have to produce star R as a superstructure. So it's something which is extremely uncomfortable for a lot of practitioners, but for other practitioners, it's extremely comfortable, on the contrary. Reflecting on Nelson's work, Reb came to the conclusion that it was already possible to justify infinitely large natural numbers at the level of Brouwer's rejection of the excluded middle. So Reb observed, which is a classical observation, any non-standard mathematician has done it, that if you have infinitely large numbers, you already have infinitesimals, because you, for alpha, an infinitely large number, you consider 1 over alpha, and it is infinitesimal, as long as you have the construction of Q. But in IST is a conservative extension of ZFC. So IST causes no consistency problem. So everything you can do in ZFC, you can also do in IST. Reb, he came to this conclusion with a small argument that I heard him expounding in front of a lot of audiences. And I remember that he was always telling his argument very slowly. And I connected with the previous intervention because he insisted on the slow pace of philosophy. So maybe Reb, by telling his story so very slowly, was already a philosopher. So he said, let us consider a formula of the type exists n such that P of n. So, and n here is meant to be a variable circulating in the natural numbers. And he says, maybe we have a proof of exists n such that P of n, but maybe it may happen, he says, for every naive natural number, and he was calling naive natural numbers, everything that we reach to, if we start from 0 and we add 1 indefinitely. So in other texts, people are calling that intuitive natural numbers. And he said maybe for every naive natural number k, we have no constructive confirmation of P of k. So but we have a formal proof of exists n such that P of n. So what does it mean? It seems to mean that our formal proof points to a natural number which has to stand beyond every naive natural number. So this would be an infinitely large number. So in Nelson's book, Predicative Arithmetic, Nelson comes to the same conclusion using Gödel's incompleteness theorem. And there is another paper from a Chinese mathematician called Liu, Liu, I should say, maybe, I don't know. Liu. And he does the same. And one can verify by looking at both their propositions that they are working exactly on the same proposition. So Reb understood the foundational situation, and he heard in this situation the implicit teaching that three facets of mathematical logic had convergent meaning, that these three facets referred to the same gap. So what he had in mind was non-categoricity of first-order theories with infinite models. This is what Robinson uses in his approach. Syntactic incompleteness of theories rich enough to express arithmetic, that Gödel's incompleteness theorem, and Brouwer's criticism of the excluded middle. Because what I just described, that we have exists n such that P of n, which is formally true, but for every constructible k, P of k is not constructibly true. It's exactly the reason why Brouwer rejects the excluded middle. But the point is that Reb saw in this foundational situation, which he analyzed philosophically, because to assert that these three gaps are the same is a philosophical assertion. He saw in this situation the implicit recommendation for a new research program, because Reb also intervened at the level of strategic entanglement. For example, before Nelson's IST paper, he told his students that they could live star R as the same as R without fearing any contradiction on the road. And so soon after, the students of Reb discovered Nelson's axiom schemes, and they felt that Nelson had just formulated the theory of their practice. And more importantly, Reb understood non-standard construction as taking up Brouwer's vision of a constructive skeleton. So this is something which is difficult to imagine for a lot of people, and maybe especially in the US, because in the US, Robinson was understood as a super champion of the big game of the infinite in set theory. And champion, sorry. I said it wrongly. And I think this vision is still important nowadays. And on the contrary, Reb saw that the deep content of Robinson's approach was that there is a constructive skeleton inside mathematical objectivity, and that it doesn't mean that we work with this skeleton and inside this skeleton, that we have to limit ourselves to that skeleton, but this skeleton is still important. And Reb understood Nelson's theory as formalizing the constructive level, because he understood the predicate, the new predicate of Nelson, ST, as a formalization of the constructive level. ST of X means X is constructive, or an approximation of that. That's how Reb understood Nelson's theory. There were some reasons for that, because, for example, in Nelson, you prove that any nameable object in ZFC is standard. And you prove also that there is a strong connection between the class of standards objects and the class of finite objects. For example, all naive natural numbers are standard. A set is finite standard if and only if all its elements are standard. And which is difficult to accept, there is a finite set, but finite in the sense of ZFC, containing all standard objects of the universe. So in Reb's vision, our usual ZFC formalism is simply a way to complete the constructive skeleton by adding all possible infinite totalities. You have the skeleton, but you are allowed to introduce any kind of totality made of these objects, of the objects of the skeleton. But then in Nelson's formalism, each time you have an infinite totality, which is superimposed to a constructive skeleton, this infinite totality is witnessed internally by a non-standard element, because you have an important theorem of IST, which says that every infinite set contains at least one non-standard object. So so Reb imagined a new research program. You can use IST in order to study ZFC's infinite totalities in their relation to underlying constructive skeleton. So there is nothing wrong against what Brouwer happened to have said sometimes, at least. There is nothing wrong in wanting to study the hierarchy of ranks. So all the magnificent construction of various infinities by Cantor. But Reb's program was to study, to accomplish this study always by having in mind the relation of all these infinite statements to the constructive skeleton. And there were some applications of this research program: discrete geometry, non-standard asymptotic, differential equations in natural numbers, and radically elementary probability theory. So these were four applications of the program. And in the 90s, there was great hope that this program could be significant and endorsed by a lot of mathematicians. Nowadays, we know that very few people engage that program, and so for now, it's a failure because nobody followed. It's a kind of failure. But in every kind of applications I just named, one had the impression that it was interesting because mathematical idealization appeared more continuously with the constructive skeleton. Because in our usual ZFC discourse, when you are introducing an infinite totality, you seem to deal with a completely different layer of entities. So it makes your discourse in a way discontinuous with the constructive layer. And in the IST discourse, very often you can bring back this discontinuity simply to the admission of an infinitely large natural number. So Reb, in his reading of the foundational situation and his deriving from the foundational situation a new research program, was overcoming the usual weak aspect of foundational entanglement, because foundational studies, no mathematician can really turn her back on it, because as a mathematician, she knows that legitimacy is a real issue that she cannot disregard. But at the same time, we have the feeling as mathematicians that foundational entanglement does not seem to relate to the exciting part of mathematics. And the exciting part of mathematics is the part where objects and problems are all the time reinvented. So Reb managed to derive a vision and design a research program out of foundational entanglement, reaching strategic entanglement in that way. So I should stop, maybe. No? I can finish? Okay. I prefer in a way, but so my second example is a case study, is category theory and Grothendieck's contribution. So I begin with the foundational facet, because there is a mixing of philosophy and mathematics also in the foundational guise connected with this category theory emergence. We know that typical categories like groups, topological spaces, or ordered sets go beyond the size of actual sets. So that's why in the talk about categorical logic, there was mention of a small category, because a small category is the category which is a set already, so which is small enough. But usual categories are not small. They are too large. And for the Bourbaki squad, it was a difficulty. They felt that it was impossible to publish a treatise on category theory before having a good solution to that foundational difficulty. Grothendieck himself thought he could deal with the difficulty by reasoning inside something he called a universe. And if you look at Grothendieck's definition, it's not far from an inaccessible cardinal. So there, if you listen to discourse of categorizations, of contemporary categorizations, a lot of them consider that there is no problem at all. We know, we experience every day that categorical discourse raises no difficulty. We may even speak about the category of all categories or the category of all functors. No contradiction will ever arise. That's an example also taken by Pierre Cartier. So, but Pierre Cartier, I come to him again, usually says that interesting and relevant category theory is always connected to an underlying rich set theoretic configuration. So he says that category theory, that he loves category theory, but he loves it only when it enlightens rich, difficult set theoretical configuration. And Jean-Pierre Serre seems to say exactly the same. So if we hear them, it looks like mandatory to reconcile the two languages. So if you accepting that you have to reconcile category theory and set theory, you can imagine to do it the other way around, not by adapting set theory in such a way that categories find a place in set theory, but translating set theory into category theory, making the category theory the most fundamental, giving yourself, choosing category theory as the foundations of mathematics. So the idea is to interpret ZFC, or sometimes ZF, into the theory. Alors, it may be the theory of well-pointed purposes. The best candidate seems to be ETCS, the elementary theory of category of sets, of the category of sets, which is the category of well-pointed toposes with two additional properties. Anyway, some people say, I'm thinking of Lovier here, which has been already mentioned, that it may be that category theory offers anyway a better notion of set. Here, people may think of the evolving sets of the topos set exponent omega. You know, it's the topos of sheaves. Yes. Yes, it's the topos of sheaves on omega with set-valued sheaves. So there is an already substantial debate about all these issues, and I don't want to evoke it more precisely. Now I come to the strategic facet, because many scholars describe Grothendieck's work as already philosophical, without having to stop being mathematical. For example, these are the words exactly that Jean-Jacques uses, I think.
Jean-Jacques is Jean-Jacques Szczeciniak.
Yeah, Szczeciniak, I should say. Well, so he's a colleague of ours. So
Was also in Chapman.
was also in Chapman.
He was in the origin of the Grothendieck.
And so he says so, but surprisingly or not surprisingly, many philosophers think the same way. I've received phone calls from philosophers who were excited because they heard about Grothendieck, and they told me we have to do something in philosophy about Grothendieck, because Grothendieck is an event, philosophical event. Okay, I think there are two ways of thinking so. The first one is related to the issue of space, the second one with the issue of architecture. I begin with the issue of space. Grothendieck may be said to have brought a philosophical contribution to mathematics by introducing the notions of scheme and of topos, which revolutionize the thought of space. We find the claim in Récolte et Semailles, harvest and... Oui, mais there is a translation I saw. I forgot. So it's page 65. He says that there is the old Mr. Space who didn't realize that he was out of date, and because there are two young garnements. How should I say that in English?
Not guys.
Ouais. Two hooligans, something of that kind, who are already showing that the old Mr. Space is out of date, and these two hooligans are scheme and topos. So you have two things to say about scheme and about topos. About scheme first. The notion of scheme may be interpreted as a new version of the object of algebraic geometry, because algebraic geometry used to be the branch of geometrical study of the sets of roots of polynomial equations, and then it was redefined as the study of algebraic manifolds, and Grothendieck changed and puts it to be the study of schemes. And it's true that if you read, for example, in David Mumford, a small red book, which was popular in the beginning of the 70s, and in which we learned the basis of algebraic geometry, he says at the end of the book that he quotes something from Hasse, and he thinks that in this quotation of Hasse, there is also already the anticipation or the desire of schemes. So, so here you would say that the notion of scheme witnesses for internal hermeneutics of mathematics, and this hermeneutics would bear at the same time on the object of algebraic geometry and on algebraic geometry as a branch. And then, why do people count the introduction of scheme as philosophical? It could be because it deals with the general issue of space, because space would be regarded as intrinsically philosophical, or it could be because it is hermeneutical. And then in that case, hermeneutics would be the signature of philosophy. I also mentioned the topos notion. So the topos notion, as Grothendieck went to it, may be taken as based on a generalization of the notion of topological space through the notion of site. Because when we have a site, we have morally the same thing as a topological space without having a set of points. So, but Alain Cohn, another Fields Medal, sees things differently. For him, I think what he has in mind is more precisely the topos of a scheme, which is a very complicated construction. And what he thinks is that with Grothendieck, we still have at some level a spatial framework, but this framework is parametered by a topos, able to let the frame vary. So the topos is a name for encompassing a lot of possibilities, and these possibilities are going to vary the frame, the spatial frame. So why is such thought philosophical? Because it reinterprets space again. So because of space, because of hermeneutics, or because it stages variation in a new way. So it would be, this part of Grothendieck would be a segment of Hegelian mathematics. Because here I follow more or less Lauvier, because Lauvier understood category theory as the reintroduction of a Hegelian motto in mathematics. Now I come to architecture. One could mention here something like the problem of motives inherited by mathematicians from Grothendieck. So Grothendieck also gave a strategic contribution to mathematics by asking the mathematicians to find a category of motives. And it's another rationale for taking mathematics to be already philosophical. It's the architectural rationale. If mathematics is interested in its own architecture, it becomes philosophy, according to this vision. Because the conjecture concerning the category of motives, from what I understand, is grounded on the observation that important cohomological theories show an analogy. So this is an architectural reflection. We have other programs in contemporary research which are based on an architectural vision of mathematics. The so-called Langlands program works at bridging number theory and representation of groups. I have heard Serre saying that in the Langlands program, you have a lot more. It's a kind of a way of unifying a lot of mathematics. In Caramello's theory, dealing with Grothendieck's toposes, we associate a classifying topos to any geometric theory within mathematics. And sometimes two different geometric theories may have the same classifying topos, And according to Caramello, they should be bridged. They have something in common. And sometimes what theories having the same classifying topos have in common may be grasped at the level of a property of the classifying topos. So I read two examples, one given by Laurent Laforgue and another used by Olivia Caramello herself. I don't understand clearly in both cases.
The point is made in Olivia paper from the.
Yes, but yes, I think she says that completeness for a geometric theory corresponds to amalgamation property for the classifying topos. But Laurent Laforgue says differently. He says that so some geometric theories I forgot about have in common that their classifying topos satisfies the Morgan law. Probably they are both right, but one has to understand why they are right. Life is long. Anyway, Caramello's theory introduces a research program, so it's strategic, not only because it's an architectural reflection, but also because there is the research program of bringing to the fore a new kind of analogies between theories crossing various branches of mathematics. Gromov's H principle, as little as I understand what it is, has also something architectural, because the idea seems to be to solve partial differential equations through homotopy. So I come to my conclusion about fruitfulness. So when we regard such mathematical gestures as already philosophical by themselves, does it provide examples for philosophy proving useful to mathematics? Or should we read the usefulness relation here in the other direction? Because if mathematics show as philosophical, is it a way of philosophy to help mathematics, or the contrary? It's difficult to say at first sight. Strategic entanglement of philosophy and mathematics is sometimes revelatory of the action of hermeneutics inside mathematics, showing that something philosophical happens in mathematics. In other cases, strategic entanglement exhibits as philosophical a new universal view. In this sense, category theory is by itself philosophical, or a self-reflection at the architectural level. So none of these cases allow us to speak immediately of an actual usefulness of philosophy for mathematics. But all of them show strategic entanglement as fruitful, both mathematically and philosophy, I would say. Because when we have a new universal layer, it helps formulating and solving new problems. An architectural reflection motivates new work as well. Internal hermeneutics is similarly a way for getting mathematical advances. Foundational entanglement may also be characterized as fruitful. On the one hand, our way of writing down the framework for all mathematics is fruitful as such. On the other hand, it provokes, although in an indirect way, a lot of developments. Let us only think of set theory and how it changed the landscape. Set theory was introduced as a new foundational framework, but it provoked a lot of new mathematics. Anyway, as I suggested, a better understanding of fundamental legitimacy is fruitful for a discipline so much concerned with providing justified results. We have seen that with George Reb, foundational entanglement could also motivate some guidance up to the point of inspiring a research program. This lays down a connection between two kinds of fruitfulness. So we did not say much in what precedes about the possible fruitfulness or usefulness of mathematics for philosophy. So my first conclusion was that the strategic facet of the mathematico-philosophical entanglement is fruitful, even if it doesn't show usefulness of mathematics for philosophy or the contrary. But then you have the other question of is mathematics fruitful or useful for philosophy? One could say that mathematics dealing its own way with universality, strategy, or hermeneutics may suggest insights to philosophy about the same topics. For in my work, grasping an internal hermeneutics inside mathematics has led to a different understanding of hermeneutics in general. Here, mathematics works as an illuminating case. But I would end up with two remarks. We all know since Plato that mathematics is a good preparation for philosophy. And for me, in a sense, there is a mystery here. We are sure that mathematics helps organizing universal attempts and making them more relevant, but we don't see clearly how it works. I'm sure of this fruitfulness or even usefulness, but I don't know exactly how it works. So I come back to what I told you was one of my conceptions of philosophy as arising from mathematics. I was defining philosophy as the project of extending universal classifying discourse from the region of the object to the region of the thing. So one could say that mathematical work gives more experience of what extension may mean. Because in order to enter philosophy, we have to extend the mathematical project. But mathematics teaches something of what extension in general means. For example, sets was an extension of both number and figure, which were the traditional objects of mathematics. And I think to understand this mathematical gesture of extending the region of the object from this double characterization as figure and number to the general characterization as set, it tells something about what an extension may mean. Also, anyway, mathematics defines the limit of the object, because what is considered as an object within mathematics is exactly what philosophy has to transgress in order to extend the project of a universal classification. So mathematics is helpful both as a model and as a limit. And these are my concluding words.
Thank you.